Alright, so now we're going to talk about vapor pressure and partial pressures of a gas mixture. So first off, vapor pressure. So what is it? Well, keep in mind, when you have a liquid, evaporation can occur without boiling. So boiling is just the maximum temperature you can get a liquid to. And then adding more heat just makes it evaporate faster. So, cancels out. But you can have evaporation occur without a liquid boiling. And so one example of this would be swimming pools. So swimming pools tend to have autofillers because water is going to evaporate. Now, you can go in the pool and be totally fine. It is not 100 degrees Celsius in the pool. So clearly evaporation is happening at a lower temperature. So we have to replenish that water or the pool level drops and the chemical levels in the pool get out of whack because the volume's changed, so on and so forth. The opposite of a dilution, you're removing solvent. So what's happening here? Well, if we have a sealed container, I can bust out multiple colors and preserve my last good black marker. And we have a liquid, right? Well, it's going to have some particles evaporate into the gas phase. So everything up here is gas. Now this is a sealed container. How do you know it's a sealed container? Because I'm writing sealed container right next to it, with a little arrow pointing to it. And so what happens is some of the liquid evaporates. Some of the molecules are hot enough that they have enough speed that they just they escape. They have like an escape velocity. They're moving fast enough that they can get away from their neighbors, and they go in the gas phase. Then they bounce around the gas phase, and eventually they might pop back into the liquid, but another molecule will pop out. And so there's a pressure associated with this gas, this vapor. We call it the vapor pressure. And it's not something that we're going to calculate. We're not going to calculate a vapor pressure. But we are going to talk about some general trends with it. So first off, a volatile liquid is a liquid that's going to put off gas particles. Some liquids are non-volatile. They just don't have any gas particles until we get them really, really, really hot. So generally we consider it volatile. If at room temperature it does this. And so it has a vapor pressure. That results from evaporated molecules that are in the gas phase. Now what happens is, if we increase the temperature of our liquid, the molecules are going to start moving faster, and more of them are going to have escape velocity. So we're going to end up with more particles in the gas phase. More particles in the gas phase equals more pressure. So increasing temperature is going to equal an increase in the vapor pressure. And you can look at the table in the book and confirm this. Because there's a table for the vapor pressures of water. Now, what happens if we just keep increasing the temperature? Well, vapor pressure is going to keep going up and up and up. But if we increase temperature far enough, that the vapor pressure reaches the atmospheric pressure, well, that's boiling. And you can't make the vapor pressure larger than atmospheric pressure because it's in equilibrium with its surroundings. And so that's why we have a boiling point. And so this is why there's different boiling points at different elevations. So if you go up way up in the mountains, or if you ever look at the cooking directions for something like, I don't know, anything you got to boil water for, like top ramen or whatever, they'll tend to have different cooking directions, or you have different baking directions for altitudes greater than 2,000 or 3,000 feet. I forget the exact cutoff. And the reason for that is that the boiling point gets to a lower temperature. Because the atmospheric pressure goes down, the vapor pressure meets that lower value at a lower temperature. And so if you're way up, like 4,000 or 5,000 feet up there, your water might be boiling at like 70 degrees Celsius, which might not seem like a big deal until you're eating some crunchy ramen noodles. If you've ever done backpacking, don't ever do the instant chili, because if that doesn't get hot enough water, oh boy, it's just grit. Let me tell you, from experience. All right. So the vapor pressure equals atmospheric pressure, and the liquid boils. So it won't get hotter. It'll stay at a constant temperature. It can boil faster. You add more heat, it will boil faster, but it will not get hotter. Alright, so that's the deal with vapor pressures. Basically, volatile liquids can be both liquid and gas, and so if it's not a sealed container, if it's an open container, the gas just escapes, and then more liquid replaces it and escapes, and so on and so forth, and eventually all the liquid evaporates and goes away. That's what goes on there. Alright, so what about partial pressures for gas mixtures? Also known as Dalton's Law. Okay. Well, remember that gas particles are going to act totally independently of each other. And so if you have a container and it has our total pressure in it, again, I'm going to lean on my markers over here. Looks like we got red and green. This will be it'll be a Christmas gas mixture. Alright, let's say we have 1, 2, 3, 4, 5 green. So these are two different gases. 1, 2, 3, 4, 5 red. Well, this total pressure, because again, they're acting independent of each other, I could figure out the pressure of one gas and the other gas and then add those two gases together. So like maybe I've got my green gas here, we'll call that A, red will be B, and so this is just the pressure exerted by these red gas particles. Alright, and this would be just the pressure exerted by the green gas particles. So the red and green aren't interacting with each other. And so I could do PV equals nRT for the green. I could do PV equals nRT for the red. I could solve both of those for P, add those together, and I'm going to get the total pressure. So the whole is just the sum of the parts. The more gas particles of A I have, the more of the pressure it's going to be. The more gas particles of B I have, the more of the pressure it's going to be. If I increase both of them, they're both going to increase the pressure because these are not flexible. So volume isn't changing. It's a solid walled container, but so pressure is changing. And so this is known as the partial pressure of gas A, because I just put an A there. And this is the partial pressure of gas B. So each of them contributes a part of the total pressure. And so, for example, in our atmosphere, the air that's all around us, well, there's N2. So there's a pressure associated for the gas particles of N2 and O2. And it's like 78% this, like 21% that. And then there's a little bit of the other stuff like argon. There's some CO2, more every day it seems like. H2O, if you live somewhere with humidity. So not a lot of that here. You add all that up, you get the total pressure. That's the pressure of our atmosphere, which is generally about 1 atmosphere. You got it, or 760 millimeters of mercury. And so there's a portion of it that's associated with this gas, and this gas, and this gas, and this gas, and this gas. You add them all up, you get the total atmospheric pressure. Alright, so, we're keeping it pretty general with these ideas. There's some very complicated stuff you can do with them, but we're not gonna. So now we're going to kind of go into gas stoichiometry. So we can use the ideal gas law, PV equals nRT. It's got N in it, it's got moles. That means we can do stoichiometry. And that's what we're going to do next.